Hi, everyone. Basically, we're going to go through how to build a Pong playing AI. How many people think they're going to actually be following along with the tutorial, like from a code point of view, like installing all this stuff? You know, show of hands. So I've never tried this on Mac, but apparently it should be very easy on Mac. TensorFlow should run with CPU version just by kind of installing it. On Windows, so if you're on Windows, the best option you've got is, I don't actually have examples in Theano, but Theano and TensorFlow are very, very close. So you can try and install Theano if you're on Windows. And if you're on Linux, that will be the easiest version, but you also then need an NVIDIA GPU. So how many people have NVIDIA GPUs on their laptop? Should have got an NVIDIA GPU. Should have done that. So is anyone installing right now? Like, I'll give it maybe like 2-3 minutes for people to kind of install stuff. Okay, I'm gonna start, and if people want to keep trying to install it as I go, I'll try and speak quietly so I don't distract you. All right, so this is building a Pong playing AI. Google DeepMind recently got the world's best performance at learning a variety of Atari games. And in this talk, we're basically just going to go through how they did it, some of the theory behind it, and share a few implementations. So the subjects we're going to cover, we're going to very, very briefly touch on neural networks. We're going to go through reinforcement learning, Q-learning, TensorFlow in a bit of depth, and convolutional networks. Why Pong? Because it's a classic, simple, dynamic game. You can train to play it in a reasonable amount of time. And the task here is to get the computer to learn it just from watching the image. So it has no access to the coordinates of the objects ahead of time. It does not know ahead of time what a ball is or what a paddle is. It's just got to learn, like a human at some point in their life must learn, by just looking at a thing and working out this is what's going on. Why do we care about this? It's fun, it's challenging, we can develop generalized learning algorithms that could apply to many other fields, and it will allow us to build our future robot overlords who will one day inherit the Earth from us. Resources, we've already talked about resources a bit. The GitHub here has all the kind of internal resources for this, so there are a collection of examples of the different bits that we're going to cover in the talk. Linux is not a requirement because you can do this on Mac, and you can do this on Windows, but then you're going to be limited to Theano, and hopefully at least some of you can follow along, but if not, you can always kind of like complete the setup afterwards, and this will be on YouTube and stuff. Pygame is a popular Python games framework. There's thousands of free open source games, and they're all written in Python, and so that means it's quite nice if we're writing our learning agent in Python, we can just move into our game, and we don't need to muck around with Atari code or anything. Pygame Player is just a little project that me and another person have worked on that allows running a Pygame with zero touch. So for a lot of examples of reinforcement learning, you see they actually have to hack the game code to change it to return a screen buffer and stuff like that. Pygame Player it basically intercepts the screen buffer as it's coming in and then intercepts the key presses. So it just handles all the kind of framework aspects for you. Oh, and it allows you to run the game at a fixed frame rate. So you can say run at 10 frames per second or 20 frames per second. It'll just always be running at that speed no matter how long you take to kind of compute. So normal Pong is 640 by 480. So for the purposes of this, I've built mini Pong. If I just go to... Actually, let me go. So mini Pong is just a very small version of Pong because it'll be 40 by 40 when I actually run it. And this means that you don't have to do downsampling of the screen to feed it into the agent. And then to make it even simpler, I've developed half Pong. To a machine, even Pong can be hard. And half Pong, there's only a single bar. So all it has to do is hit the ball. And then it gets points just every time it hits the opposite wall. And hopefully this might be able to train in like the length of time that this takes if you kind of started training it now. If anyone wants to do that, they could try that. Otherwise, you could do it after. And let me just really quickly show half Pong running. Oh, and that's the big version. So that's half Pong. And then if I change the screen resolution, never mind. OK, so the first example for this we're going to show is just random Pong. And random Pong, there's the example here. And that way, we're just going to randomly move about the screen, hitting keys within the range of normal Pong keys. And that's going to give us a baseline for how well the agent does. So if I go to the first example, here's random Pong. And it's just completely randomly moving. And it will occasionally hit the ball, hopefully, and get a few points. But this is pretty bad, and obviously showing no real intelligence. Here's how you would implement it. It's pretty simple. So you just inherit from the Pygame player base class. And in the start method, we just set it to run. We pass in the screen dimensions. And that will handle all the other stuff for you. And then here, the getKeysPressed method is called every time the screen is refreshed. And then you can set in what keys you want to be pressed the next time it asks for keys. And then the one thing we need to supply with a game is we need to supply a feedback function. Because it's a bit mean asking it to learn a game just from looking at it. It also needs some kind of feedback to say when we scored a point or when we lost a point, just so it has something to learn off, because otherwise, what is success? How good is random half Pong? It's not very good. It scores like negative 0.03, so significantly less than 50%. So now we'll go through a few examples of trying to improve it. So first, let's try using neural networks. Who here kind of knows a bit about neural networks? Do we have reasonably, that looks like most people. So I'll pretty much skip this, except to say if you don't know about neural networks, for the purposes of this, it's just like a thing that is able to approximate complex functions. So here's the implementation for an MLP, a multi-layer perceptron half Pong. We're going to set the number of frames per second to 6, which is there. Yeah, you do get the cursor. We'll have this, which is going to create our network. And it's going to give us back an input layer and an output layer. The input layer is what we're going to feed the screen buffer into, and the output layer is what we're going to get, basically a score for each potential action we could take. In Pong, the actions are we could hit the up key, we could hit the down key, or we could do nothing. And the neural network is going to try and assign relative values to each of those, and we're going to select the highest value action it gives us, and that will be the action we take. Who has used TensorFlow before? Do we have a few people? Who's used Theano before? Very few more. Oh, yeah. So I won't cover this in too much depth, but basically, TensorFlow under the hood is a computational graph. So we're going to give it a set of variables and operations it's going to perform. And then it will take those variables and put them through the operations, and it will come out with an output. But we set up this graph ahead of time, and then it will basically compile everything down and put it on the GPU if you've got one, or the CPU, and allow us to run things like ridiculously faster than they would if they were run through another mechanism. This is just creating a very simple 3-layer neural network with ReLU activation functions. So we're going to give it a set of variables for the first layer weights and the biases, and the second layer weights and the biases. We're going to activate it. We're going to do matrix multiplication between the input layer and the weights in the first layer, and then the weights in the second layer, and then we're going to get an output. Doubled that up. Cool. And then here is so in random Pong, we were just randomly selecting a move. Here, what instead we're going to do is we're going to take the binary image. We're going to just sample it down, so it's, rather than being RGB, it's just 0 or 1 for like active or not active for every screen pixel. We're going to feed that in to the agent, and we're going to take the max action, and we're going to return action key to index. And now to do something really, really stupid, here is that Pong set up with a multi-layer perceptron, and it got lucky there, but basically this is awful now because we've not actually done any training. This is just like a random, being fed random numbers and failing, as you can see. So how does it do? How does it do? Awful. We need to train it, but what is a loss function for the game of Pong? Does everyone know about loss functions? No one knows about loss functions. So in neural networks, there's 3 types of learning. There's supervised, unsupervised, and reinforcement learning. Supervised learning is we have labels for data, and say we have a collection of images of handwritten digits, like the MinSet dataset, and we have labels for which handwritten digit each of these images corresponds to. When we put the pixels through our neural network, it's going to give us an output for which label it thinks applies to each image. And the loss function is the difference between what the neural network thought the image was and what the image actually was. And then we can use the loss function to retrain the network and use what's called stochastic gradient descent to kind of push the various errors that it got back through the network and retrain to eventually get the correct values. But something like a loss function doesn't work in this context because it's going to get periodic feedback from like the ball being scored against it or it conceding. But that's not a loss function. We don't know what the correct action would have been. It's just some noise at the moment. So in reinforcement learning, which is the kind of field we're going to need for this, agents run with an environment. They take actions. They receive feedback. They aim to maximize good feedback and minimize bad feedback, and computer games being a great way to kind of train reinforcement learning agents. The kind of most, or a very common approach with reinforcement learning is genetic algorithms, which have been incredibly successful. But the thing that's a bit kind of rubbish about genetic algorithms is humans do not learn through genetic algorithms. You know, we were not born with the genes to play Pong. We were born with the genes to learn Pong. So we want algorithms that can actually learn in the same way that a human might learn, or are able to learn these kind of new things, not just randomly look through possibilities and find things that happen to do well. So this is where we come into Q-learning, which is the approach we're going to use for making this work. Given a state and a set of possible actions, the Q function will try and determine the best action to take to maximize our reward. Any action we take will put us in a new state that has another set of possible actions. Our best action now depends on our best action will be in the next state, and then the next state from then on. For example, here is a bunny, and he's going to be dropped into this maze here. In state 5 here, if I go down to it, state 5, there's a carrot, which will be equivalent to 100 reward. And the Q function is going to try and learn which action is the best to take to continually get to the carrot. Here's after optimization, but I just wanted to jump through to the Q function. So here's what it actually looks like. R corresponds to the reward in the state we immediately move to after the action. And this is a discount factor, and this is the maximum of the Q function given the state we moved into in the action. And so we say we want to, oh, sorry.
Is there a similarity between this and dynamic programming?
Dynamic programming would fall more under genetic algorithms. This is all, like, the code is all written ahead of time. It's just we're going to use this to retrain the weights for, like, the particular values of different computations we're doing. So that's what the algorithm looks like. And then to kind of give an example of that with this maze, which also I stole this from someone else's website just to attribute this. In state 5, that's the goal state. So obviously, the reward for being in state 5 is 100. That corresponds to this little bit here. If you're in state 4, also the reward from state 5 is 100. If you're in state 0, well, you can move to state 4, and then the next turn, you can take the maximum possible action in state 4, and that's 100. And then we're going to have our discount factor of 0.8 in this case. So it would be the Q function for moving from 0 to 4 is 80. And the good thing about the Q function being set up like this is that moving directly from 4 to 5 is more valuable because even though you could get to 5 from taking the long way round, the discount factor means it's not as desirable because we want reward now, we don't want reward at some time in the future. And after we've optimized our Q function, our bunny will have lots of carrots. That's great. The way it's normally computed is kind of iteratively. So we start with a very bad Q function. We then go through all the possible states and update the Q function given the information we get from like what actions we take in each state. Then we then apply the Q function we've then learned, which will be this bit, to better estimate the Q value of everything in the next frame. And we'll increment everything by a learning rate. So eventually, over time, the Q function should learn kind of very accurate kind of distributions of a state space. Sorry?
How do you choose the discount factor?
Arbitrarily. Some number less than 1 because we want the future to be less good, and more than 0 because we want the future to have some impact. It falls under hyperparameter tuning, so some random number. So I'm going to show an example of this with the world's simplest game. So in the world's simplest game, we simply have a kind of a one-dimensional map. You're going to get a reward for getting into the 4th state, and all the other states you're going to get nothing for. And the agent will be placed in one state, and it can either move forward or backward. And we as humans can pretty accurately solve this maze. I think we all know you want to move to the reward space. And so we've got an implementation of this in TensorFlow. Has anyone actually gotten TensorFlow kind of set up on their laptops? Has anyone got Theano set up on their laptops? OK, we've got a few. So the amazing Leif Ferretti has also written a Theano implementation of this. So if you want to look at that, that would be great. Here's the TensorFlow one. The Theano one is just here. It's number 4. And here's the implementation. We're going to create our little kind of mini maze. There are 2 actions. You can either move forward or you can move backward. This has a 0.5 future discount rate. We'll create some placeholder values, and these are what we're going to feed in the state that we are currently in, and also we're going to get out from these targets. Oh, we're going to use these targets as the loss function when we actually train the thing. Oh, sorry.
Could you just ask if they can turn the lights off on the screen?
Can we turn the lights off on the screen?
If that's possible, but
Is it like glare?
yeah, we'll just do the middle bit of the screen, not the top bit, because it's all white.
Yeah.
Thanks, man.
No problem. All right. So we're going to set up our really mini game. This is just going to like train a linear Q function. So it's just a direct mapping from the input to the hidden weights, and it'll just be like there is some number for each value. In TensorFlow, you have to initialize variables. We're going to run through and iterate through this a bunch of times, and each time we're going to print out the value that this determines each state has. So let's just see what that looks like. And as we can see, on the first iteration, the reward for the goal square is 1.0. That's what the actual reward is. And then we already have a slight value from our Q function, which is the future discounted value of getting to the reward square, and the same for the square on the other side. And then over time, it's gradually improving this estimate until eventually we have what should be a nice distribution of the value of being in each square in our kind of mini maze, and that can be used to just, you always select the action that takes you to the highest value square. But we can try some other values for that. So that was a very simple maze. We could also make this square really bad, so the agent will try and avoid that. And so now at the end, I mean, there's still some reward for going through the negative square, but it's now pretty bad, so we don't want to be in the negative square. So that is that. Has anyone read about the Enron scandal? I'm going to go for a really, really tortured metaphor here. So we want to apply Q-learning to Pong. And I think a good metaphor for trying to get these kind of we want to make the game of Pong look like a maze with states to our Q-learning algorithm. And so in Enron, the way in which the accounting department would make all their money is there are rules about how you can book something as profit or loss. And so what they would do is they would take something that was clearly a loss and they would make it look like something that could be profit. So they would book it in a certain way, they would file it through a certain offshore company, they would file it back through another company. So that is a metaphor for what we're about to do here. We're going to try and make Pong look like that silly little one-dimensional maze game. So did that metaphor make this easier or harder to understand? I really like that metaphor, but I wonder if it's awful. In Pong, the normal screen size is 640 by 480 pixels. That's going to be way too big. That's like a huge state space. That immediately is 2 to the power of some massive number of different states. And then also, Pong's a dynamic game, so just knowing what the current screen looks like doesn't really allow us to tell what's going on in Pong because the velocity of the ball changes. So we want to get a few frames into our state space so that it can learn, the velocity. If we were to choose, say, 4, then the number is still too big. So we're going to use neural networks to try and reduce this state space into something more manageable so that our Q-learning algorithm can learn this. So now we have the MLP Q-learning half Pong player. And as well as Q-learning, we will need experience replay. So we don't just want to learn off what the current screen looks like, because that would take ages. We want to basically store all the states we go through in memory as memories. And then when we're actually learning, we can do mini batch sampling off of that. Does anyone know mini batch sampling? Rather than training off a single example, we're going to train off a batch of examples, and that will just learn quicker. So we're going to collect the states, that's experience. We're then going to sample from them and then learn off that, which is replay. So this is an example of, we take our binary images, we do something special with the first frame, and then for subsequent frames, we're just going to append our new image to a big array with all the previous images in it, and then store that as an observation. Training, so this is basically exactly the same algorithm as for the kind of silly little 1D example, but now we have these huge arrays that represent the whole screen, and we'll train off those. And the one difference is in Pong, there is a terminal state, so if the ball hits the far wall, the game is going to reset. You're going to go back to the normal position. So there's not much point predicting what your reward will be after the reset state. The reset is just the end of reward, and then you start a new state. And that's training. And the only other thing we have to do is, at first, our Q function will be really bad, because it's just going to be started with some random initialized weights. So we want to start with taking completely random actions. And then over time, hopefully, as our Q function improves, we'll substitute more and more random actions for chosen actions from the network. And then eventually, we'll just be running chosen actions. And that should give, at that point, that should be a good distribution of things to learn off. So how does it do? Let's see a trained network running this. So there is mini half Pong. And then let's take a closer look. Woo. So you'll see this is doing better than random, but not significantly better than random. So that was awful, but there's movements like that that are clearly not random movements. It's going for the ball. It's learned some kind of pattern out of this, and that was pretty good as well. But there's a lot of work to be done. You can see the score down at the bottom there. It's scoring very slightly positive, so way above random, but still not that great. Why is that probably not doing that well? The reason that's probably not doing well is because there's no linear mapping from the screen of Pong to the actual actions that we take. What we actually care about are the kind of relative positions of things. It doesn't matter if the ball is in the top half of the screen or the bottom half. What matters is where the ball is relative to our bar. And linear or shallow mappings will not be able to tell us this. They're just going to be going off the kind of absolute position of activations in the network. And so, like everyone has heard the term deep learning kind of passed around everywhere. That's a fair assumption? One of the things with deep learning is it's kind of automatically allowing us to learn features, but also it's allowing us to learn invariant representations. So the idea is the more layers we have, we'll start to get to layers where they're not just learning individual activations, but they're learning things that don't tend to vary as far as the higher layers are concerned. So this will allow us to learn things like the position of the ball relative to the bar is a factor as opposed to just the absolute position of a thing. And the other point of this is convolutional nets in a bit more depth. That's the other thing we're going to be using here as the kind of the first few layers of our network. The thing with convolutional networks is, or the insight as to why convolutional networks are good, is we as humans know that if we take the pixel in the top of this U, the things that give the meaning of U to that pixel are very unlikely to be pixels over here, or pixels over here, or pixels over here. When we're talking about like what the meaning of something in an image is, what we really only care about are things really, really close to it. It's very unlikely that something in an image is actually correlated with something very far away at kind of that lower level. So a convolutional net basically will start off by detecting features just in a very small space of the image, and it will, like a sliding window, kind of move across the image and compute things that it can get from just the few pixels around the kind of central point. So that's what we're going to use here. So here is the implementation of the convolutional net half-Pong player. Very briefly, in TensorFlow, there is a conv2D method, and we can pass in strides, which is how far we're going to move across each dimension as we're going. And we're going to put this together, and this is hopefully going to be a bit better at playing Pong. So how does it do? Should we run this up and see? Let me stop the previous one. So let's see, and hopefully this will do a bit better. And let's zoom in. So how's that? Somewhere. Okay. No, come on, do better. Do better, there we go. Okay. So you'll have to believe me, this isn't looking so great right now, but it scores significantly better than than just the kind of shallow network. You can also, the checkpoints for this network that are saved are kind of available on the GitHub, so you can kind of run it yourself, and you can also try training from scratch to kind of see that. But if you just take my word for it, this is about like 30% above. It's scoring, what is it, like 65% of points here, which is not too bad. So how does it do? It's amazing now. It's amazing. That was amazing, right? Right, guys? Sorry.
How many layers?
So let me go. Well, actually, no, I can do it from here. Let me go back to the code. So we have a convolutional layer. We have a max pooling layer. We have another convolutional layer. We have another max pooling layer. And then we have two just normal kind of neural network layers, all with ReLU activate. Huh?
It's like a linear 5
Yeah. The DeepMind one uses like a third convolutional max pooling layer, I think. But this is my laptop, so I had to make savings. So now it's amazing, and now our future overlords are pretty close. That's the next step. The same architecture can be used on all kinds of other games. So this has been used on Breakout, Qbert, Sequest, Space Invaders. Cool, thank you. Hope you enjoyed this. Any questions? Oh, thank you. Yeah.
I was wondering for the optimization, did you use a stochastic gradient descent with mini-batch, or did you play with like momentum method?
So this is using an Adam optimizer.
Okay.
I've seen RMS prop used as well. I think it also works with gradient descent, but like, there's so many things you could try. This has worked, so I've not messed around with it until after this, just so I don't screw things up. Any other question?
You said the main reason to use convolutional net, convolutional networks, right, is that those pixels are correlated. Like, why not checking which pixels? Is a computational reason?
Close pixels, they're not definitely correlated, but they're much, much more likely to be correlated. So, the shape of a letter is going to be dependent on the pixels next to one of the pixels in the thing. It's very unlikely that there happens to be an association between like a pixel in one letter and a pixel like on the far side of the screen. So, in some sense, and this is like, there are loads of other ways of looking at it, but in some sense, what a convolutional net is doing is just giving you like a few activations in the small area that are much more likely to be connected, as opposed to like having to check every neuron against every pixel, rather against every other pixel, where they're very unlikely, or there kind of almost shouldn't be connections between the further away pixels. Yeah.
So as the movement of the ball is like always in a straight line, do you reckon it would sort of work better if we operate on a differential of images, consecutive images, or do you reckon that would be cheating?
Sorry, let me come across. Sorry, what was that?
Oh, sorry. So the ball moves in a straight line.
Yeah.
Do you reckon it would help if you sort of train this differential of consecutive images? Would this be cheating?
Yeah. That is an approach that could be tried. I don't think that would be cheating. I think the main thing is, though, we want something that works not just for Pong. We want, or ideally, well, actually, no, you can do whatever you want. Yeah. It wouldn't be cheating. It probably would, or it could work quite well. I don't know. It would be worth trying. Any other questions? Has anyone actually managed to run this while I've been talking? How did it do? Or how's it looking?
It was complicated because you got to move the resource and comment folder into the example folder, and then it's Python 2 code, so you got to change.
Yeah.
Running, so you got to change the grid to records, and then you have to install OpenCV as well.
That as well, yeah.
The resource folder is not built into the.
Yeah, it's a submodule. Because you successfully did it, can I grab you after this and you help me make the setup steps actually workable? That would be great. Thank you. Any other questions? Oh, sorry.
I think in the last few months there's been quite a few reinforcement learning libraries bringing up
Yeah.
all around the world, like I guess notably this GIM. I wondered if you sort of plot that and sort of offer any perspectives on that.
Oh, yeah. OpenGym looks really, really great. I'm definitely going to try putting a few things into there just to see how it is. But also, OpenGym is not like a reinforcement learning library. It's a reinforcement learning environment library. So it doesn't provide any algorithms. It's just a really, really good space for trying out algorithms, getting them peer reviewed, seeing what other people have done. It sounds really great, and I'm definitely going to be playing around with it at some point. Cool. Any other questions? I've got another half hour, so it's going to be really boring from now on, unless someone asks a question or something. What bit did I explain awfully? Were there any bits that were just that you have no idea what I was talking about? Yeah, so that.
Probably a training slide really fast. Can you just explain that one?
What, the algorithm for training?
Yeah.
Okay, let me go back to the TensorFlow one first. Actually, you know what? It'll be even better. The Q function versus the TensorFlow implementation. Okay. So that is the the Q function bit. So in this set, as we're going through this iteration of the thing, we're going to create each state once, and this one hot just encodes something as 0, 0, 0, 1, 0, 0, and 1 is the state we're actually in. We're then going to get, so the minus action and the plus action is just what would happen if I move forward or backward through the network. Then here, so our output here is basically the output of a queue function. So we're going to use our network as it's been trained up to this point. Let me just kill that. We can use it as it's been trained up to this point to estimate the Q value of what it's being given. And that step corresponds to this thing in here. So that's that bit of the Q function. We're going to grab that. We're then, once we have the two actions that it could have taken in from its current state, we're then going to take the max of the actions from there. So that bit is the max. We're going to times that max by the future discount reward, which is gamma here. And then we're going to append or add to that the actual reward received in each state. So 0 in all of them except for 1 in the reward state. And then the loss function is the difference between that and what our network thought it was previously. So it'll just, it will adjust all the weights to kind of learn that. And then the example in Pong is almost identical, except we just have the concept of a terminal state. So if we get into the terminal state, like there's no future reward, you're dead. That's it. Was that better? That was better? Cool. Any other questions? Any other bits that were just like I did not explain at all? Any other bits that made no sense? Yeah?
This is not actually necessarily about but so you mentioned a couple of the deep learning frameworks.
Yeah.
Could you offer any perspective, especially like TensorFlow versus Theano? What's your take on that?
Yeah.
Any opinions?
So I've gotten really into TensorFlow. Part of why I like TensorFlow, actually, so Lei might be able to have some input here. She did the Theano implementation. TensorFlow has the nice thing that you can just say, you can create an optimizer. Where is it? You can create an optimizer and you say like, I want to minimize this thing. Theano has some of those things, but it's kind of just, it's harder, that training bit to do in Theano. You often have to do more bits by hand. Theano is quite a lot faster than TensorFlow still, but I kind of feel like I wouldn't bet against TensorFlow because it has Google behind it. It's got huge community support. So if you, I've been talking to one of the guys at Google who works on TensorFlow, and he's been like the most helpful person in the world. Like they are committed to like getting people on board with this library. So kind of like community support matters quite a lot for any library. Theano, you don't get the same kind of response if you ask questions on it. And just because it's backed by Google, I wouldn't bet against it. I mean, it's probably going to become a kind of a pretty de facto standard, and DeepMind are switching to it, and other people are switching to it. So that would be my 2 cents. Cool. Yeah.
How did you come with the size of the layers, where numbers are random?
It's a very good question. So DeepMind the DeepMind paper quotes like numbers in the layers. I'm using fewer in here because I've made the screen even smaller. So I just kind of cut out a layer from their one. It seemed to work. This is one of the frustrations with this stuff is, I mean, actually I can show you. So I've got another example here, which is like a kind of big proper, like full scale thing. And I had the idea that I would show this today, and I was trying to train it. Let me open another thing. I was trying to train it like last night and stuff like that, and hoped I could show like a full-size one. But it just it hasn't worked. It's like I'll show it now. It's awful. It could be awful because I just got unlucky and it got into some weird local minima. Oh, sorry. Let me switch to playback mode. It could be awful because hyperparameters are wrong. It could be awful because there's some bug in there. It's very hard to know. It's kind of, at the moment, it's a case of like find something that works and then don't mess around with it. But I'm sure there will be better approaches to this developed in the future, or I really hope so. Yeah, this is not doing great. I don't know what's gone wrong here. I wasn't going to show this, but I've showed this as an example of it not working. So it serves that purpose. And in fact, I'm going to stop that playing because it makes me feel sad. Let's go back to the one that worked. Yeah, that actually works. Yeah.
The number of pixels on the small one versus the big one, what's the...
So this is 40 times 40. The other one is 640 by 480, but then I'm using CV2 to downsample it to 80 by 80. I think the Google DeepMind paper actually quotes they downsample it to 84 by 84, I think, or something like that, but that kind of range.
Maybe it's just a matter of taking much more time to train.
Well, this is I thought so, but I kind of like, so when I went to bed last night, it was looking quite good, and I got up in the morning and it was awful. Maybe more, I think it might have just got stuck in some kind of local minima, or just something has gone wrong. Maybe if I start from scratch and do it again, it'll be fine. Just the weights were bad. It's hard to tell.
You use early stopping?
No, but
I could have stopped it at the right time.
well, this is yeah. Well, I thought it was going to get better. Yeah, early stopping, great idea. Yeah, TensorFlow does a thing of saving previous checkpoints, but it's like I'd left it overnight, so it only saved like the previous 5, and even the earliest one was still a bit crap. But that works. Yeah.
At the beginning of the learning, you use random motion.
Yeah.
You place progressively apply with learned motion.
Yeah.
It makes sense to have a human player at the beginning that gets progressively replaced. Would there be any chance of it? You learn later.
Yeah, no, I mean, because basically the thing you want is like what you want is like the best possible distribution to learn off, like what playing good Pong looks like. The reason you start with random is because the computer hasn't learned it yet. If you could actually learn off a good player, that would probably be even better. But obviously, then someone's got to play Pong for like a few days. It's not that fun a game. Wouldn't recommend it. Yeah.
I suppose you class this as a hyperparameter question, so I'm wondering about convolutional layers, how large a region you can choose for your kernels, whatever you call them. Also, you mentioned that you need to see a few frames per row for this. I think different games require you, remembering and comparing.
Yeah.
Is there any work where that can kind of be learned, like how far back you look, what you pay attention to, or just like what kind of kernel you use?
Yeah, I've not read of any work like that. It's possible. As to like the convolutional layers, let me see what I've ended up with. This was kind of like half taken from the DeepMind paper and half like kind of hacked about. So what's that? 4 versus 4. Oh, and also someone also posted quite a lot of the code for the DeepMind thing that I borrowed heavily from as well, just to attribute. These are the weights for the. That's what the variables look like for the second convolutional layer. That's the first one. So you'll see it's going to go down from a 40 by 40 screen to an 8 by 8 with like 32 sets of features, 64 in the next line. I think that's similar to what DeepMind used. There may be better options. There may be worse options. It would take really, really long to train lots of networks and see which are better, unfortunately. Yeah.
In a practical sense, so really TensorFlow and Piano, they can play with switch from CPU to GPU.
Yeah.
And so if you play with like simple problem like recognizing the gentleman is whatever, CPU is fine on a laptop, but at which point of complexity you need to switch to GPU, otherwise you won't be able to train a model. What level of
Well, I think you can always train at CPU level. Like it will be, but it will just take ages. Depends how long your thing is. I had an implementation of this in a previous laptop which only had a CPU, and the difference in speed, like things that were taking me like days on the previous laptop, I could do in minutes on this thing. It was also an old laptop, but even if it's an old laptop, like you're getting orders of magnitude improvement from a GPU. If you want to be doing this seriously, you're going to want a GPU at some point, or like space on an Amazon, cloud server or whatever.
You said at the beginning you took 4 consecutive frames, but with Pong, everything is pretty much moving in a straight line at constant speed.
Yeah.
So I'd have thought 2 frames would be sufficient. You don't actually get any more information from.
Yeah. So when I first built this, I tried it with 2 frames. And it was doing terribly, so I switched to 4. Then I realized the problem was some completely unrelated bug. It might be if I try this with 2 now it works, I just haven't had time.
Bouncing won't work.
You think bouncing won't work?
Well, if there's only 2 frames and it bounces, it won't work.
Possibly. No, because you know which way it must have bounced. There's only one option for kind of.
If you're doing it in a straight line, if it bounces against the wall and then comes back down, you don't know whether it's gone in a straight line
Yeah, but it's unlikely. So if we're talking about we're near a wall, we've got the two things here, it's like that's the only possibility. It can't have gone all the way to the other wall and back. Oh, you mean a directly straight line? Possibly. I think there's kind of set, like this ball can only move at certain sets of angles. It can never go quite straight. But it varies, I don't know. 4 is working, and I'm kind of like, until, you know, like I was doing this today, it seemed really bad luck to start like mucking around with everything just before I did this, so I've stuck with things that were working.
Daniel, sorry, yeah, I wanted to ask a question on, this has been sort of engineered to make Pong work, but of course, you know, you could write software that doesn't include any neural nets to make Pong work, right?
Yeah.
So, to what extent is this like applicable to other games? You know, if you just put Pac-Man on it, would it work? You know,
Yeah.
what kind of
So I've not tried this myself yet. I've just been mucking around with Pong. The Google DeepMind paper, they cite like 27 games, something like that. And they show that it performs very well, like human level or better, for like a significant number of them. So the ones I mentioned in the slide were ones that it did really well on. So Breakout, Qubit, Sequest, Space Invaders. And apparently that is using like exactly the same algorithm, like no changes to the number of layers. Obviously, you retrain the weights, but it's exactly the same code. But it also performs very badly on a lot of other games, so there's more to be done. Yeah.
Concerning that, something that you said, well, I will use a screen instead of having the position of the tile because that's cheating. But you are accessing internal state when getting the score of the game.
Yeah.
So I guess for each of these games, you have to in some way cheat for this.
Yeah. Without some kind of.
Or they have some.
So what they use is, I can't remember the name of it off the top of my head, but it's called the Atari Game Playing Framework, and they've already like built in those little signals. Just without those signals, like there is no way for the computer to know what is a good or bad response. I don't know. As humans, I think we intuitively know that like you hit stuff with a ball. That's what you do because we've learned that as babies or something. So we don't need to be told that, but that's.
Asking because there actually was some studying around that they play in Nintendo games.
Yeah.
And instead of having specific signal, they were trying to get. They were running on an emulator, so they have the
Yeah.
access to the hardware.
Yeah.
And they were trying to get variables to get higher values.
Yeah.
That was
Just.
generic measure that worked for several games.
Okay. Yeah, I mean that sounds like a good way of doing it. I mean, the other thing, Keith O'Stanley, I think, had a whole thing on novelty search. So one of the ideas is rather than optimizing for like some variable if you don't have it, just try and optimize a thing to look for situations that do not look like previous situations. So I'd love to see someone try something like that, just optimizing for exploring basically. Do we have another question? Oh, yeah.
Would it be possible some way to extract information for this neural network which have been trained to recycle the most difficult larger screens sometimes? For instance, hitting the ball is a common principle.
Yeah. Oh, you mean like take a portion of this and put it into something else?
No, take something which is a fruit of learning.
Yeah, I mean, there's a whole field called transfer learning, which is about getting nets that have been trained on one thing to work with another thing. And there's a lot to say, but like that's a whole field. I'm not sure how much I can add right now on that. It's like, people have tried it, and there are ways in which you can have some level of success with things like that. Cool. If no one's got any more questions, I think I'm going to sit down, because it's just weird if I'm just standing here. Oh, sorry, yeah? It probably would. You would need to add like a new layer somewhere with new mappings, but I think that would almost certainly work. Yeah, I'd be surprised if it didn't. But then you never really know until you try with these things, because things that look like they really, really, really should work can not work, because it's still an evolving field. Anyone else? Oh, yeah? Oh, I thought you put your head, you went like that. That's all right. Okay, cool. Thank you very much, everyone. I'm going to sit down now. That was really great.